Hello and welcome. I'm Regina Hebig, and I will present our work on how students experience and judge software comprehension techniques. As you can see, we are a large team of authors, including Trong, Rudi, Jan, Humberto, Magnus, and Salome, who I all thank for their contribution. So why are we asking this question? As software educators, we have several long-term goals when it comes to our education in general and specifically to comprehension techniques. Of course, we want students to grow up to be professionals who have an overview about the field and are also experienced with diverse approaches and strategies to comprehend software. However, our field is changing with the time, so it's really important that our students stay curious once they are out of university and they stay aware of state-of-the-art developments. And of course, we also want them to think critically about the new tools that are coming out so that they can identify those new techniques that actually fit their use case. And this has implication for education. We argue that students should use and experience different techniques while they are still at the university. But furthermore, we argue that at least some of these techniques that they experience need to be truly helpful to the students already while they are at the university. Because otherwise we're simply running the risk that they, will think of these techniques as academic, maybe even esoteric, and are unlikely to look back later on when they are professionals. And finally, this also means that we as educators need to have an understanding and also communicate with the students what techniques might be immediately perceived as useful by them during their studies already, and what techniques they should be aware that they right now don't get so much out of it, but later they will get much more benefit of them. We studied students' experience and judgment of comprehension technologies in the context of a 15-credit capstone project course in software evolution. The students here work half-time for 16 weeks on a project in teams of 4 to 5. They are presented with a legacy software system that they should recover, comprehend, refactor, and extend during this whole time. The schedule on the slide shows the first 7 weeks of the course. As you can see, we have some lectures here, namely on program comprehension, clone detection, and refactoring. Each of these lectures includes small exercises that we are actually performing with the students in class, and it is followed by a larger individual assignment where the students are asked to apply the techniques that they have learned in class to their project system. During the lecture on software comprehension, we are providing an overview about diverse techniques and related fields. As you can see, for example, on this overview slides that they typically show to the students. The more focused active lecture parts and later assignments are focused on the systematic code reading, reverse engineering, software visualization, and documentation generation. And for the later 3, we also introduce tools to the students. Regarding the project that the students work on during the whole course, we use different projects over the years. For example, in 2018, we had an external customer who had a legacy system that they wanted to be recovered and extended. And in 2019, we used McGill's Qualizer, which is an open source system which had last been in 2012 released. And these systems typically have a size of around 300 files. At the end of the 5th week, we have a first milestone with the students where they should actually demonstrate the comprehension of the system that they have reached by that point in time. And during the system, the students are actually asked to present their understanding and answer questions about the system. And then whether they have reached this milestone or not is immediately assessed and documented afterwards. So after they've answered the question, we signal them, okay, you've passed the milestone, we put the information into the system so that they can see it immediately. And only after that we start with the reflection session, because for us it is important that students know that they're not graded on their opinion about the tools that we presented to them, because we don't want to threaten them. So students are invited to really critically reflect about the tools that they've used, the tools and techniques, and to judge them. And in 2018 and 2019, we made notes during this reflection session, and afterwards asked the students whether we can use this in an aggregated form, to which 20 teams agreed. And of these 20 teams, 13 teams were from the batch in 2018 and 7 teams were from the batch in 2019. So let us look at some of the results. Documentation generation received actually mixed reviews. So in 7 teams, we had discussions that considered it somewhat useful as it provides an overview about the system. But in 10 of the teams, we had discussions that the technique is kind of cool, but not really useful. And as a main hindrance, the students mentioned that there's a lack of useful comments and meaningful naming in the code, and with that, the generated documentation does not have the same value. We found a similarly diverse picture for reverse engineering. So the first interesting thing here is that students actually went far beyond the tools that we showed them in the lectures. So we actually mostly showed them how to generate class diagrams, but they went out and actually found tools to generate data flows and dependency diagrams and all types of things. These diagrams were judged by students in 12 teams as useful to gain an overview about the system. And one team even mentioned that they used them in order to guide the later code reading. However, we also have students that have a bit more different perspective. So in 5 of the discussion, reverse engineering was considered to be only partially useful. And in 10 of the discussion, it was mentioned that tools for reverse engineering are too limited. To our surprise, software visualization was something that was really little discussed and little used by the teams. So we mostly here introduced code cities simply because this is a technique that's easily accessible and also one that got really positive research already around it that is showing benefits of it. However, we had only 2 teams and 2 team students that actually considered the code cities themselves as useful to them and to their comprehension. And in contrast, we had 7 discussions where they were clearly named as not useful. And all in all, students mentioned the wish to be able to switch more between different abstraction levels here. And then finally, systematic code reading got the most positive feedback from the students. So students would perform this to understand the flow of the code as well as details. The teams used diverse strategies to actually approach the systematic code reading. So we would have teams that would go in and follow the references through the code. And we would have teams using diverse artifacts like the file structure, the search functions, and error logs in order to support their understanding. Some of the teams even used models, documentation, and SonarCube outputs as guidance. So they would go, for example, back and forth between a model, look at the model and for certain model parts, and then at the corresponding code and back and forth. And finally, some of the teams tried to trace between code and user interface. And all in all, the teams agreed that it was very easy to perform, but also very time consuming. Besides our 4 main techniques, students also talked about other things, of course, in these reflection sessions. And one of the most surprising to us was the big value that was attributed to SonarCube, which is a measurement and analysis dashboard. So in 11 of the discussions, students actually mentioned that they gained a quick overview through using the SonarCube. And examples mentioned here were mostly that it helped them to identify the risky parts of the system, because SonarCube mostly highlights, for example, technical depth. But they also reported that the clone detection functionality, for example, helped them to understand aspects of the architecture. So for example, with the clone detection, they could see what components in the system actually fulfilled versions of the same functionality. However, in 3 of the discussions, it was pointed out that about 90% of the features are not considered to be useful to software comprehension, which is of course not a surprise because we did not introduce it as a software comprehension tool. Another aspect that was mentioned was refactoring. So we had actually students who felt that they gained knowledge by performing changes to the code, so by refactoring the code and observing the consequences. And even more extreme, we had a few students that reported to systematically change code all over the system in order to gain a first understanding. We had also some teams that discussed the importance of the user perspective for comprehension. They would, for example, run the system, they would put in effort to collect domain knowledge, and they would really trace user interface elements down to the code. And then finally, timing was a topic during several of the discussions. So for example, The students propose that you maybe should run the system before you actually start reading the code. And I would also say you should, or some of the students would say that you should read the code before even starting with the reverse engineering. On the other hand, documentation generation and debugging, that two techniques that were mentioned, that should be really happen much later in the process. To discuss some highlights, SonarCube was surprisingly helpful for our students. So we think it is worth considering adding these tools to regular software comprehension curriculum. Also, educators should consider whether to teach software comprehension not just as a collection of techniques, but really as a process. So to communicate to the students that these techniques should complement and build on top of each other, and that they might become more useful after having done other steps already. From a research perspective, we were surprised to see that not all techniques lead to the same positive results as related work indicates. This holds, for example, for code cities. One possible explanation could be that many of the techniques we introduced actually fill the same niche. For example, many tools seem to provide a good overview. It would be interesting to study how this overlap in functions affects the perceived benefits of techniques when used together. Another explanation is that many studies rely on collecting typical questions asked by developers. However, there's a difference between questions asked by novices and questions asked by programmers that are already familiar with the system. And our students, setup students were clearly novices. Our students had also a comprehension need that went further than just answering some questions, because they had to build a whole project on top of their comprehension. This might have implications for empirical research on comprehension techniques in general. Similarly, it indicates that it might be difficult to actually teach and create a positive experience for comprehension techniques that are targeted at more advanced questions of comprehension. To summarize, we studied how students experience and judge software comprehension techniques. We did this in context of a project course on software evolution, and in this talk I presented an excerpt of our results and discussed some implications of our findings. Thank you very much.